Screen. Yes. Okay. Hi everyone. Hi. So let's. Any question? Any question? No. By the way, about your proposals, I will check them. I will check them and let you know my feedback. I faced some lack of time. Whenever I can, as soon as possible, I will check your proposals and will give you my feedback. I will give you individual feedback as well as in general feedback on Learn. So that's about proposals. And yeah, okay. So last session, we started game theory. Let's review that very briefly, and then we continue. So what did we say? Let me bring it. It's a bit hot here, all right? What should we do? I don't know. So that's also hope. I don't know. Sorry about that. The temperature, I don't know what's going on here. Okay. So we started game theory by saying that what the elements of a game are. So for example, we said what game theory is, then players, agents, right? And action, payoff or utility, information, a strategy. And we said the payoffs are functions of strategy. We talked about equilibrium, but we didn't say how to find the equilibrium. Today we will talk about it. And outcome of a game, nature, which is a non-strategic player in the game, and which does random things but with known probabilities, right? Action set, action profile, cooperative game, non-cooperative game, with conflict, without conflict. We mentioned some examples for them, even from the movies. By the way, another game which I just came to my mind, another movie for cooperative game with conflict, which is a horror movie. Have you seen? Can you give me some example? Have you seen the series of Saw? Saw 1, Saw 2, Saw 3, etc. I have heard that recently the latest Saw has come to the cinema, and I'm a fan of Saw actually, and I think it's very cool. This Saw, although it's cringe, but it's interesting to see a cooperative game with conflict. They are cooperating with each other not to die, but they have conflict sometimes. A lot of horror movies are cooperative games with conflict. Okay, representation forms of a game. We talked about normal form, which is like a table or matrix, right? Having the payoffs, and extensive form, which is like a tree, right? And we said it's a bit different from game tree, where game tree has the outcomes at the end nodes, but extensive form has the payoffs at the end nodes, right? Also, we talked about some well-known two-person games. So examples are Prisoner's Dilemma, where there are two prisoners which are going to be in jail, and they're asked by police officers. The other game was Game of Chicken, where two young people drive toward each other and one of them should swerve. The one who doesn't swerve sooner will win the game, but they might both be crazy and die at the end. And we also talked about Grab the Dollar, two variants of it. So one of the variants has been used in the Let's Make a Deal, a TV show, and it says that we have some dollar and they need to either decide whether to split it or to be selfish and get the whole dollar. We talked about whether they can be fined or not if they both grab the dollar. And we also talked about battle of sexes, where a couple of man and woman decide to go out. The man wants to go to the Fight Club show, the woman wants to go to the ballet show. And if they cannot consensus, then they cannot go out and they kind of lose the game, both. The other one was boxed pigs, where we said that there is a dominant pig and a submissive pig or a small pig, and there is a control panel at one side of the box and some food dispenser on the other side of the box. And whenever we push one of them pushes the control panel, the dispenser will dispense some food. And we talked about different cases where one of them presses, the other one waits, or both press, or both wait. And as the pigs are different, this game is non-symmetric, right? The previous games were mostly symmetric, but this one is non-symmetric. And we also said this is, by the way, we said that these games, we see them a lot during the daily lives. This game, for example, is the game of bullies in high school or middle schools, right? So the other game which is a very famous game, is ranked coordination, where, for example, we have two companies, computer seller, floppy disk seller, and they should decide whether the computers to accept large floppy disks or small ones, but the floppy disk seller should also decide whether to make large floppy disks or small ones. Of course, they should match, otherwise they will both lose the market, right? And by the way, we'll see more coordination games in this lecture, hopefully. And another game which we discussed, I think this was the last game that we discussed in the previous session, that was the welfare game, where we have a social democrat government such as Canada who wants to aid a pauper if they are unemployed, but they are looking for a job, so they are not lazy, right? And we said there are several cases. The government can aid or not aid. The pauper can look for a job or not look for a job, right? So the actions, by the way, are different. In some games, the actions of the players are the same. I mean, the action sets. But in some games, the actions are different for the players. This is an example of different actions for the players. And then we also said that the government wants to aid, but doesn't want to be fooled by the pauper. And the pauper also wants to get the welfare, but maybe tends to be lazy. So, but as we saw, the games are showcasing the different difficult scenarios, right? The hard scenarios, they are not usually easy to find out which is the best thing to do. Okay, the next game, which we are going to talk about, we didn't talk about this in the previous session, is the Battle of Bismarck Sea. And this is a battle in the World War II. And I apologize if it's not appropriate, but this is a famous game in the literature, so I didn't make it up. So you can Google the Bismarck Sea to see which countries were on the sides of this battle. So the Battle of the Bismarck Sea during the World War II in the South Pacific in 1943. I think by South Pacific, you can guess which countries were involved. Okay, so someone named General Imamura, if I can pronounced correctly, is in one side of the war, has been ordered to transport his troops across the Bismarck Sea to New Guinea, if I can pronounce these words correctly. Then General Kenny, in another side of the war, wants to bomb the troop transports. Okay, so one of the generals wants to bring his troops, and the other one wants to bomb them. Okay, so Imamura should choose between a shorter northern path or a longer southern path to New Guinea. Right, so we have the northern path is shorter, the longer path is the southern path is longer. Kenny also should decide where to send his planes. Kenny wants to should decide where to send his planes to look for the Japanese. Sorry, I forgot to erase that word. For the other side. So in other words, one of the sides wants to bring their troops. The other side wants to bomb them, but so both sides should decide whether to go from north or south. Kenny, Imamura, what happened? Imamura says whether my troops go from north or south, and Kenny should decide whether to send his the airplane, you tell me, his military airplanes to north or south. Okay, so of course, if Imamura goes to north and Kenny sends to south, it's bad for Kenny. If Imamura sends to south and Kenny sends to north, that's bad for Kenny also. Kenny wants to try to imitate where the Imamura goes, but they are ordering simultaneously, so they don't know which side will do what. If Kenny sends his planes to the wrong path, he can he still can recall them, but the number of days of bombing will be reduced. Okay, so this is the kind of hertz that he will see. Therefore, if both chose the same path, Kenny benefits, and it is bad for Imamura, right? If they choose different paths, Imamura benefits, and it is bad for Kenny, because Kenny can still recall his planes, but the days of the bombing will be reduced. In all cases, the payoff of Imamura is negative. Why? Because his troops will be bombed anyways. Agree? Anyway, but in some cases, they are less bombed. Agree? So sometimes, in some cases, it is less negative. In some cases, it's more negative. Also, north is usually better for Imamura. Why? Because the northern path is shorter. So let's see the payoffs and see whether they make sense. So if they both send to north, of course, it's good for Kenny, bad for Imamura, and if they both send to south, it's good for Kenny again, bad for Imamura. But we know that north is better for Imamura because north is shorter. Therefore, we put -2 for north of Imamura and -3 for south of Imamura. As a result, it's the opposite goes to Kenny, right? 2 go for north of Kenny and 3 for south of Kenny. Now let's see to the other 2 cases. One of them is, so if Imamura sends his troops to south, but Kenny sends to north, then what happens? So again, the Imamura will be bombed less. As a result, he gets -2. Why -2? Because -2 is better than -3. Sorry. Let me think. Why -2? Of course, it's better than -3 because if they both send to south, the Imamura's troops will be bombed for a longer time. So -3 for longer bombing. As a result, it should be better than -3. So we put -2 for south of Imamura. The opposite goes to Kenny, 2, right? And what about this case? If Imamura sends to north, Kenny sends to south. Of course, Kenny gets less than sending to north because he can bomb the troops for less number of days, right? So 1 should be less than 2 here. And the opposite goes to Imamura. Also comparing these two, of course, minus both north is worse for Imamura than north-south, right? Because both north will be bombed for longer days. And what about comparing this column and this column? You will see that overall, the payoffs of north for Imamura are better than payoffs of south for Imamura because north is shorter path. Okay, so the whole payoffs make sense. Any questions? Interrupt me if you have any. Zero-sum games. So one player's gain is with the other player's complete loss. So what do I mean? Whenever we have zero-sum games, I think it's obvious by their names, but it's a family of games where whenever one of the players gets the payoff, the other player loses completely. So I can say that the summation of the payoffs becomes 0 at every case. So of course, in this case, they have conflict. The players will have conflict, and their payoffs are kind of have opposite sign, right? Because their summation should be 0. So this is called zero-sum game. Because can you give me an example of the game where we don't have zero-sum game? Some scenario. For example, an example of zero-sum game is eating a cake. An example of zero-sum game. We have a cake, we should split it. If I take the whole cake for me, you will get nothing, right? If I get half of it, you will get half of it. If you get whole of it, I will get nothing. Always the summation of our payoffs becomes the whole cake, right? So it's zero-sum game. Whenever you get everything, I get nothing. So this means this is the zero-sum game. Whenever one player gets everything, the other player gets nothing. Okay. Can you give me an example of non-zero-sum? This is a scenario coming to my mind. We have a murderer, a psychopath murderer, for example, and some normal person. Okay. The psychopath murderer wants to kill a normal person. Okay, that's fine. If they kill the normal person, so the normal person will lose everything, right? You might say the psychopath murderer also gains everything because at least for some moments, they will get happy for one moment. Maybe they get sad later. But we know that the murderer doesn't get everything. Why? Because they will be in jail later, right? So they will have some loss afterwards, or at least will be escaping the detectives, right? This stress, right? So I'm saying that the murderer doesn't get everything. They will lose something also, but the normal person lost everything. This is not a zero-sum game. Agree? Can you give me some other examples? No? What? Prisoner's dilemma. Why? Can you tell me? Let's see. Is it non-zero-sum game? I don't remember. I don't memorize the games, and I don't want you to memorize the games. Just try to understand it. Prisoner's dilemma. Okay, you're right. The summation doesn't. So well, when they both cooperate, as you see, so whenever it's zero-sum game, the payoffs should have opposite, their absolute values should be equal, and they should have opposite signs. Here we don't see this, right? For both cooperate, they are both -1. For both defect, they are both -2. Whenever one of them cooperates, the other one defects will have -3 and 0, right? So thank you very much. It's a non-zero sum game, right? Let's see if in these examples, do we have zero-sum games? I think I have shown an example in the same slide that I introduced zero-sum games. The Battle of Bismarck Sea is a zero-sum game, right? Am I right? Yeah, this is exactly a zero-sum game. Here I have said it. Is the welfare zero-sum? What? Welfare. Let's see. No, it's not. It's not a zero-sum. Okay. Or consider a magic cake that whenever I eat everything, something still remains for you. For this magic cake, it will not be a zero-sum game. Okay. We talked about introductory lecture of the game theory and some examples of two-person games. So acknowledgement, some slides of this slide deck are inspired by teachings of Professor Stanko Dimitrov. Who here is from the management sciences department? You? Only you? And maybe people watching on YouTube. Okay. So you know Professor Dimitrov? No, he's in your department. Yeah, at the University of Waterloo Department of Management Science and Engineering. So Professor Stanko Dimitrov, he sometimes offered the game theory course in the Department of Management Sciences. Well, I think that's a graduate course. I took his course, and it was a very good course. I really enjoyed that. So many of these are inspired by his teachings. By the way, feel free to Google him. Some slides of this slide deck are based on the following book, Erik Rasmussen, Games and Information, an Introduction to Game Theory. So the textbook that Professor Dimitrov teaches from is this book exactly, Erik Rasmussen, Games and Information, an Introduction to Game Theory, 4th edition. And you can see the materials of the book in this homepage. Okay, a good lecture series on YouTube I found by William Spaniel, if I can pronounce correctly, William Spaniel, about fundamentals of game theory. Its name is Game Theory 101. So it has different subtitles, such as strategic form games. Feel free to see this playlist for his lectures on YouTube. An important scholar in the area of game theory is Martin J. Osborne, who used to be a professor at the University of Toronto. I think he retired. This is his Google Scholar. Okay, feel free to see his papers. And these are the references. And this is the book that I just said. Yeah, this is, for example, a paper about Prisoner's Dilemma. This is a book in game theory published by MIT Press. And also, this is another book, Games and Decisions, Introduction and Critical Survey. And we also have, you can see this book just for coordination games. You remember the ranked coordination? There is a book on that, published in 1999. As you see, game theory is a bit old, but it's very interesting. Okay, let's go to the next topic in game theory. Any question? No? Yeah. Okay, now that we introduced game theory, its elements, and some well-known two-person games, let's talk about how to find equilibrium, right? Or in its plural, equilibria. So in this lecture slide deck, we talk about dominance and Nash equilibria. There are two different equilibria. Okay. So first, let's talk about equilibrium in general. A strategy profile, S star. So what do I mean? S1 star, S2 star until Sn star. Assume we have n players, each of which has some strategy in playing the game, right? Right? Now, assume they do things rationally. If you consider all of the strategies of all of the players, we call it a strategy profile. And if it is an equilibrium, we denote it by a star, S star, which is the best strategy for each of the n players in the game. Of course, they are rational. They don't want to hurt themselves, right? So equilibrium strategies are the strategies selected by the players maximizing their individual payoffs, given the strategies of the other players. So you can see that given the strategies of other players, what strategy this player chooses, right? These are the equilibrium strategies. By the way, you can see equilibrium as kind of convergence of the, maybe it's another name for convergence of the game, okay? When does the game end, converge, or has equilibrium? In game theory, we desire to find equilibrium or equilibria in games, right? This is a desire of game theory. Two well-known types of equilibria exist. We have dominant strategy equilibrium and Nash equilibrium. Okay. So let's talk about them one by one. Dominant strategy equilibrium. We define S minus I to include the strategies of all players except the ith player. Okay. So basically, what do I mean? So do you remember I said put all of the strategies next to each other to become a vector of strategies, right? Now eliminate or exclude Si. So go from S1 until Si minus 1, then jump to Si plus 1 until Sn. So you have eliminated Si from. We denote it by S minus I. Okay. So basically it means that the strategies of all players except the ith player. Right? As the players are assumed to be rational, right? The ith player's best response to the strategies S minus I, so or the ith player's best response to the strategies of other players chosen by other players is a strategy Si star. So Si star is the best strategy in response to other strategies, resulting in the most payoff for the ith player. Of course, the ith player wants to have the most payoff, right? Given the strategies of other players. So what does it mean mathematically? Let's see. So it says the payoff, payoff of Si star and S minus I, right? By the way, it's important that in S minus I, they are not a star. Okay, they are not a star. So basically, for finding every Si star and I, you can sweep it from 1 to n, right? You see what others are doing, and then you decide what to do. That's your equilibrium. The next person also does that. The next person also does, right? So Si has a star, but S minus I doesn't have a star. That's an important thing. Pi I, Si star, and so we know that the payoff of the I player, pi I, is a function of both its own strategy and the strategies of other players. That's why it's a function of Si star and S minus I. Yes.
because empathy is based where based on the role of the player is score is found against the score is
So you're saying you're questioning why we don't have a star from S minus I?
I'm just
The greater than or equal?
Yeah, like that. Some players score as given the function of the role.
Yes, so we don't say that always games have equilibrium. Sometimes the game might not have equilibrium, and we'll see some examples. But if all of the players can maximize their payoffs, then we have convergence. In other words, first off, let me answer you in this way. You have a bunch of payoffs for each player, right? In the table, for example. Can you sort them? To sort the payoffs. So one of them is maximum. Right? Agree? So the players can find their maximum payoff. But I'm saying that we should also note that not necessarily all games have equilibrium. Sometimes they don't have equilibrium. And we will see in the same lecture, hopefully, that we have pure strategies and mixed strategies. What do I mean? We'll see. But let me give you a heads up. Pure strategy means that a player does some action purely, right? Mixed strategy means that let's make it probabilistic. Okay. With some probability, this player will do this, and with 1 minus that probability will do the other action, something like that, if we have two actions. Right? So this is mixed strategy. Some games don't have pure strategy equilibrium, but they have mixed strategy equilibrium. Okay, so we'll see that. But for now, in this slide deck, we're talking about pure strategy equilibrium. Okay. So, any other question? No. So, pi I, the payoff of or utility of the ith player is a function of Si star and S minus I. We know that, right? Then we can also consider other strategies which are not equal to Si star, and we denote them by Si prime for all of them, for all other strategies Si prime, which are not equal to Si star. If this inequality holds, then the player Si is happy with that strategy, right? Because whatever strategy the ith player chooses except Si star, its payoff might not be maximized. Agree? Right? Is there any confusion? No? Of course, everyone wants to be happy, wants to increase their payoff. If you have doubt about it, look in the real world life. Everyone wants to benefit, right? So, dominated strategy, what is that? A strategy of the ith player is a dominated strategy. We denote it by SID. D stands for dominated. If it is strictly inferior to at least some other strategy of the ith player, okay, regardless of what strategies the other players choose. So sometimes for the ith player, we know that this specific strategy is dominated. It's worthless to do. If the ith player does that, we'll lose something, will not benefit. Hence the name dominated. It's dumb. And it is strictly dominated. So as you see, less than, not less than or equal to. Let's go into the math to see what. So we talked about English, now go to math. What does this mean? There exists. Okay, there are at least 3 important things in math that you should know notations. This is for all, because this is inverse A, right? All. For all, this is exists, there exists, right? Because it's opposite E, exists. And this is exists a unique. So what's the difference of exists and exists a unique? exists a unique, it means that there is only one. Exists means at least one. So there exists means at least one. It can be two, it can be three. Exists unique, so this means unique in mathematics. Then it means that we only have one. It exists and there is one of it. Okay. And so we know these things. Now let's see. So here we saw for all in equation 2. Now in equation 3, we see exists. So there exists some, and it's not necessarily unique, right? There exists some a strategy SI prime where pi I SI D and S minus I is less than pi I SI prime and S minus I. What does it mean? Whenever the player I plays the strategy SID, which is dominated, it is less than, strictly less than the payoff if the same player plays the strategy SI prime. And if we find at least one SI prime, that SID is dominated, right? If at least one of the strategies of the ith player dominates some strategy of the ith player, that strategy is a dominating strategy. Agree? Let me think to give some real world example. Always try to understand game theory by real world example. Let me think. Assume we want to share a cake. The actions are, so the strategies or actions, whatever, are either we divide the cake by hand. Okay. So I might get 70% of it, you might get 30%, or I get 30, you get 70%, or we halve it, 50-50. Another case is that I become neat and go and find a knife. Okay. If I go and find a knife in the kitchen, when I come back, you have eaten the whole cake. Okay. So going and finding the knife in the kitchen is dominated the strategy, because if I do that, I will lose the cake, right? It doesn't benefit me, right? Whenever there is some strategy which doesn't benefit you, it's dominated. It's useless, right? By the way, in equation 3, we have this, we also have this. Let's talk about them. So the left side, this which says there exists at least some SI prime, right? At least if one of the strategies of the ith player dominates another strategy of the ith player, that strategy is a dominated strategy for that player, right? What about this one? For all S minus I. It means that regardless of what others do, right? What if, in the same example, real world example that I said, what if there are 3 players, right? If I go and find a knife in the kitchen, one of the players might hold the other player, says that we should wait for them, right? Again, it depends on the 2 other players. Sometimes the other player might grab the whole cake. Sometimes the third player might tell the second player we shouldn't eat, we should wait for the player 1, right? So in some cases, finding a knife might be bad for me completely. In some cases, no. This strategy is not dominated anymore. It means that regardless of what others do, for all the strategies of the other players, if my strategy is dominated, is less than one of the strategies, then that's dominated and it's not worth doing that, right? Did you understand it? Okay. Then we also have dominant strategy. Let's see what it is. A strategy of the ith player is a strictly dominant strategy, denoted by SI star, right? By the way, when we usually don't say strictly, by default it means strictly, okay? Is a strictly dominant strategy denoted by SI star if it is strictly greater than all other strategies which the ith player can choose, regardless of what strategies the other players chose. So let's see in math. So basically, in English, it means that whatever others do, let them do that. I don't care. Regardless of what others do, if I find a strategy which is better, whose payoff is better than all of other strategies that I can do, that is a dominant strategy. So it's a bit different from dominated strategy. Dominated strategy is the other way around. It says that for the ith player, if, regardless of what others do, if there is a strategy which is worse than at least one of the other strategies of the ith player, that's a dominated strategy. But a dominant strategy should outperform the payoff of the ith player from all other strategies of the ith player, regardless of what others do. Did you get it? Let's go into the math. Pi I, so both sides are the payoff of the ith player. Pi I is a function of Si and S minus I, right? But in this side, we have Si star, and in this side, we have Si prime. And we also have these two. What does it mean? First off, for all S minus I, it means that for all strategies of other players, we don't care what they do, regardless of what others do. What does this mean? For all Si prime not equal to Si star. Basically, it means that when the player I performs the strategy Si stars, it is confident that its payoff is strictly better than its payoff if it does some other strategy. Right? Is it clear? Is it clear? Right? Okay. We also have weak dominant strategy. A strategy of the ith player is a weak dominant strategy denoted by Si star. Okay. If it results in a higher payoff in some strategy profile and never resulting in a lower payoff. In other words, its payoff, in other words, its payoff is greater than or equal to other strategies of the ith player for all strategies of the other players. Moreover, its payoff is strictly greater than other strategies of the ith player for at least some strategies of the other players. I think in English, this is a case where mathematics is easier to understand than English. Let's see mathematics. So, what is it saying? First off, this equation 5 is the same as equation 4, which was dominant, strictly dominant strategy, but it's greater than or equal to. Okay. Agreed? So it's not strictly greater. It's greater than or equal to. But it has another condition too. Another condition. And what is that? There exists some S minus I. So there exists some other strategies of other players that pi I S I star S minus I is strictly greater than pi I S I prime S minus I for all S I prime not equal to S I star. Did you understand the equation 6? What does equation 6 say? It says that Si star. So first off, it should satisfy equation 5, which we talked about, to be weak dominant strategy. At the same time, it should satisfy equation 6. And what does it mean? For if the player I plays the strategy Si star, it knows that its payoff gets better at least in some other strategy that the other players choose. So not necessarily in all strategies that other players do, it gets better. At least in some strategy. So equation 6 doesn't say regardless of what others do. No. It says that at least in some way that the players play, if I choose SI star, I get strictly better. Yes. S minus I. So S minus I in equation 1 means that what others do except player I. So here we are talking about player I, where I goes from 1 to n, the number of players, right? And S minus I means that the strategies of other players except the ith player. Which one? Which equation? So what you are talking about this or this, right? For all S minus I. So basically it means that whenever we see for all S minus I, what does it mean? For whatever strategies other players do. What?
I thought S negative I already shows all the different strategies. Why is there
Yes. Yeah. No. What do I mean? S minus I, for example, assume my actions are stay or go. Okay. Then assume I have 2 players, right? Then assume I have 3 players. 3 players. Let me add a page here. Assume I have 3 players, player 1, player 2, player 3 can do go, stay or go. Stay or go. These are the actions. Stay or go. By the way, the actions might be different. For simplicity, I assume they have similar actions. Okay. So what is S minus 1, for example? It means that the strategies of all other players except player 1, right? So 1 S minus I can be a stay, go. Another one might be stay. Another one might be go, stay. Another one might be go. Well, we have at least 4 possible S minus I, S minus 1. When I say for all S minus 1, it means that for all of these cases. Right? Agreed? Do you understand? Okay. Any other question? So what basically for all S minus I, it means that for whatever the other players do, regardless of what others do, right? So going back to this slide, we said that weak dominant strategy equation 5 is similar to the equation in strictly dominant strategy, but it's becomes greater than or equal to. Also, it should satisfy equation 6. It means that at least there is one possible way that other players play. In that specific case, if I do SI star, my payoff gets maximum strictly. It gets better than playing other strategies SI prime. Okay. If we want to talk about these 2 equations in English, let's see. Assume you come to the room, suddenly you see these 2 equations. Let's interpret them. So the first equation 5 says that for regardless of what others do, so I'm also circling where I'm talking about. Regardless of what others do, if the player I plays SI star, its payoff is better than or equal to other strategies that it can choose. Okay. Right? Greater than or equal. Equation 6 says at least for one other way that other players play, if player I plays the strategy SI star, its payoff is strictly better than its payoff when it plays all other strategies SI star, which is not equal to SI star, right? Agree? Did you understand? Okay. To summarize, a weakly dominant strategy is a strategy which is always at least as good as every other strategy and better than some. Right? So this part, at least as good as every other strategy, is equation 5. Better than some is equation 6. What happens if you drop better than some? Equation 6. It's not, its value is less than dominant strategy, I believe, because at least you should be good in some cases. If you are not good in some cases, if whatever others do, you're always bad in that strategy, then why do you call it dominant strategy? So equation 6 is required for weakly dominant. Okay. Weakly dominant strategy equilibrium. So far we talked about the strategy. Now equilibrium. The strategy profile found by deleting all the weakly dominated strategies of each player. Okay. And strictly, also called a strongly dominant strategy equilibrium, is a strategy profile found by deleting all the strictly dominated strategies of each player. Basically, it means that for each player, if we eliminate the strictly dominated strategies one by one, finally we will end up with a strictly dominant strategy equilibrium, a strictly dominant strategy. Okay. And now we do it for all of the players. We put these strategies next to each other. This becomes a strictly dominant strategy equilibrium. Also for weakly is the same. So we eliminate or drop the weakly dominated strategies of each player one by one. For each player, we'll end up with some weakly dominated strategy. If we put these strategies next to each other, we'll have a weakly dominated strategy equilibrium. Okay. Okay. Yes. So now there is a good technique to find the dominance equilibrium. So far, until up to this slide, it was about mathematics. If you want to write a paper in game theory, you should go in this way almost, right? You will see these a lot in game theory papers. From this slide, now we see how can we implement all the theory that we just saw in an engineering way, okay? In an algorithmic way, let's see. So iterated dominance equilibrium is one of the algorithms to find the dominant equilibrium. One way to find the dominant strategy equilibrium is the iterated dominance equilibrium. For this, what do we do? By the way, I will show you examples, right? For this, we delete a strictly or weakly dominated strategy from the strategy set of one of the players. So choose one of the players and delete one strictly weakly or weakly dominated strategy. This reduces the game matrix in the normal form to a smaller matrix with less number of cases, right? So basically in this algorithm, we make the matrix smaller and smaller. The table is smaller and smaller by removing some rows and columns one by one. And by the way, which player do we choose? Choose one of the players, see if you can find some dominated, strictly or weakly dominated strategy. If not, go to the other player. Do it until you find some player where you can find a dominated strategy. Also, which one should we consider strictly or weakly? If you consider strictly dominated, at the end you will have a strictly dominant equilibrium. If you go with weakly dominated strategy, at the end you will have weakly dominant equilibrium. Of course, a strictly dominant equilibrium is better to find. So you go for a strictly dominant equilibrium. If you can't find any, then you reduce your expectation and go with weakly dominant equilibrium. Okay? So we perform this deletion repeatedly. It's an iterative algorithm, right? So rows and columns are removed one by one. At the end, we will end up with one cell, right? Hopefully. Then that cell tells you the payoffs of the dominant equilibrium, and the actions corresponding to that cell are the strategies of that equilibrium. Okay, we'll see examples. By the way, can you answer me, what if I do the same algorithm, but I can't end up with a cell? So I can never, so for example, I reduce the matrix from 5, assume I have 2 players, each one of them has 4 actions, the other one has 5 actions. So my matrix is 4 by 5, right? In the normal form. I remove the rows and columns one by one. At the end, it becomes 2 by 3 or 2 by 2. It becomes 2 by 2 matrix. But whatever I see, I can't go further. I can't find a row which is dominated by another row, or a column which is dominated by another column, even weakly. Then what does it mean? There is no dominant equilibrium, right? Who says that all games should have equilibrium? The world is not perfect, right? That's also philosophy. In some cases, you cannot find consensus between the players, right? They always have fights. So if we can end up with one cell finally, that cell is a strictly or weakly dominant strategy equilibrium. Let's see some examples. By the way, in these examples that I'm talking about, I have rows and columns because it's a matrix. What if I have 3 players? Can I use this algorithm if I have 3 players? Of course, yes. Then the matrix becomes like a cube or tensor, whatever we call it. Cube with height, width, and length, we call it. And then we should consider eliminating rows, columns, and heights, something, one by one, until we will find one cell in this cube. If we have 4 players, we need to imagine it. It's a rank 4 tensor, right? It's in a 4D space. So let's consider this example where we have 2 players, each of which has 3 actions. So the player 1 has actions A1, A2, A3, corresponding to the rows, and player 2 has actions B1, B2, and B3, corresponding to the columns, right? So now, assume these are the payoffs, right? The payoffs in the normal form. Let's see if we can use this algorithm. So I consider player 2 for now, randomly, right? Random. By the way, if it has an equilibrium, whatever player you choose randomly, you will end up with the same solution, okay? With the same equilibrium. You don't need to worry about which one to choose. So assume this one. By the way, there is one important thing, in one exception I can say in mind. If it has dominant equilibrium, you will end up with the same cell regardless of what players you choose randomly. What if For example, it might have 2 weekly equilibriums, right? You might have multiple weekly dominant equilibriums. Then it is not robust to choosing different random players. So maybe if you choose player 1 first, you will end up with one of the weekly equilibriums, dominated equilibriums. If you choose another order, you might end up with the other equilibriums. So it depends on whether you have one strictly dominant equilibrium or multiple weakly dominant equilibriums. Okay. So now consider this example. I choose player 2. Now what should I do? I should consider the payoffs of the player 2 in this table. So these are the payoffs. I'm drawing around them. Agreed? So I have these vectors. One of these vectors, its values should be strictly or weakly greater than the other ones. For example, here I have 3, 1, 9, 4, 3, 8. So 4 is greater than 3, 3 is greater than 1, 8 is not greater than 9. So this column doesn't dominate this one. Also, as 3 is not greater than 4, this column also doesn't dominate the second column. So neither of these dominate the other one, right? What about columns 2 and 3? So 4 is greater than 3, 3 is greater than 2, 8 is greater than -1. As a result, column 2 strictly dominates column 3, right? As I have drawn here, is strictly dominant. So I can get rid of column 3 because it is dominated. Recall the example of finding a knife from kitchen. If I do that, the other player eats everything, right? So we get rid of column 3. The table or the matrix becomes smaller with 2 columns now, B1 and B2, because I dropped B3. If I had dropped B2, what would remain? B1 and B3. This time I dropped B3, so I will end up with B1 and B2 now. And the same, other rows all the same, right? Now, assume this time I choose player 1. By the way, what would happen if neither of these columns in step 1 would dominate the other one? Then I would check whether they weakly dominate or not. If it's still not, I would give up on player 2. Go to player 1 and compare. I would compare the payoffs of the rows, right? The player 1, and would see whether one of the rows is dominated by the other row or not, right? Did you understand? Okay. So now we go to step 3 here. Randomly, I choose player 1. So what are the payoffs of player 1 in the rows? So how can I draw it? Hopefully you understand. So this is one vector, 13 and 1. This is one vector, 4 and 3. Another vector is this, -1 and 2. Agreed? Agreed. So let's find a vector, a row vector, which dominates, hopefully strictly or weakly, the other row. So 4 is greater than 13? No. This column 2 doesn't dominate column 1. What about column 1? 13 is greater than 4, but 1 is not greater than 3. So column 1 also doesn't dominate column 2, right? In other words, they are both weak. Neither of them is strong, okay? Columns, row 3. So row 2 and row 3, let's compare them. 4 is greater than -1, yes. 3 is greater than 2, yes. As a result, row 3 is strictly dominated by row 2. So I can get rid of them. Now there is an interesting observation here. In step 1, consider step 1 before elimination of the third column. In this case, does row 3 eliminate row 2? I have shown it here. I have shown it here. Consider these two rows. 4 is greater than -1, 3 is greater than 2, but 6 is not greater than 8. So basically it means that this happened, this became possible because in the previous step we had already removed column 3. Agreed? So iterations depend on each other. So that previous iteration helped us finding these dominated rows. As a result, I think you can understand, the more we go in the algorithm, the smaller the table becomes, the easier is to find dominated rows or columns. Initially, it might be harder because we have more elements, right? So the more we go in the algorithm, the easier it becomes to find. There might not be any equilibrium, but if there is any dominated row or column, it's easier to find, okay? So now we get rid of the third row, we will end up with this matrix in step 5. So we have 2 rows and 2 columns, A1, A2. Why? Because we dropped A3. So A1, A2 and B1, B2. Agreed? Now you tell me, what about this case? Assume I choose player 2. So I should consider the payoffs of the player 2. 4 is greater than 3. 3 is greater than 1 strictly. Nice. So column 2 is strictly better than column 1. As a result, I get rid of column 1. I drop B1, action B1, and I will have only action B2 and A1 and A2 here. Agreed? Now we have only 2 cells. Hopefully we can reduce it to 1 cell. Of course, if I choose player 2, it doesn't do anything because there is only 1 action for player 2, which is left. So I should choose player 1. Player 1, its payoffs are 1 and 3. 3 is greater than 1. Nice. So we can drop row 1, which is A1. If we do that, we will end up with this single cell with payoffs 3 and 3 and actions A2 and B2. So basically, this is the dominance equilibrium where its payoffs are 3 and 3 and their actions or the strategy is A2, B2, right? So it's S star. What is this S star? A2, B2, right? Now, can you tell me what if here I had 3 rather than 1 and 4, I had 3 and 4 in the cell A1, B2. So I have 3 and 4 and 3 and 3. Then this is not strictly greater than the row 1. It is weakly greater than or equal to, right? Then this equilibrium, we could still drop row 1 or row 2. Agreed? Do you agree with me or not? So I'm talking about this case. By the way, I'm not completely sure. I should check whether changing this 1 to 3, does it affect the previous iterations or not? Currently, I'm assuming it doesn't, okay? If it doesn't, and I end up with these 2 cells, then what happens? I want to compare these 2. So 3 and 3, they are both equal to each other. So we can say either this or this, right? Agree? I can either drop row 1 or row 2, right? So it has 2 solutions, either A1, B2, 3, 4, or A2, B2, 3, 3. So in this case, it would have 2 weakly dominant strategy equilibria. But this one had unique strictly dominant equilibrium. Why is it a strictly dominant equilibrium? Can you tell me? Because in all iterations, all steps, my greater than inequalities were all strictly greater than. They were not greater than or equal to. So this one greater than, this one greater than. This one greater than or less than. This one greater than, right? As they are all strict inequalities, the final thing is dominant, a strictly dominant equilibrium. If at least in one of the steps it's weakly greater than, I mean greater than or equal to, at least in one of the steps, then the final solution would be weakly dominant equilibrium. Agree? Did you understand? Yes? Why are you looking at me like this? Did you understand the algorithm? Yes? See, I need to drink some water. It's fine. Nash equilibrium. And let's talk about Nash equilibrium and then we'll have a break. So, Nash equilibrium, by the way, this is another way to find equilibrium, okay? Nash equilibrium was proposed by John Nash during years 1949 to 1953. See these papers by Nash, okay? Also see his Google Scholar page. John Nash, I can say, is the most famous scientist in the field of game theory. And there is also a movie about him, A Beautiful Mind. Yeah. And the movie concentrates on his scientific world, also his disease. He had a disease, he had schizophrenia. He used to see people who are not existing. He won the Nobel Prize because of his contribution in game theory and finance. You know that game theory is used a lot in finance. So he revolutionized finance by his equilibrium in game theory. And because of that, when he was old, they offered him a Nobel Prize of finance. And I don't know whether it's true or not, when the person went from the Comedio Nobel Prize went to tell him that you have won and to invite him, he said, be careful not to do crazy things on the stage because of his disease. And I said, don't worry about it. But yeah, at least we see that in the movie. So he was really a beautiful mind. Okay, so Nash equilibrium is named after him because he proposed it. What does it say? The strategy profile S star is a Nash equilibrium if no player has incentive to deviate from its strategy, given that the other players do not deviate. It's a bit different from dominant strategy. Okay, it's a bit different. So what did it say? Strategy profile first in English, then we go to math. A strategy profile S star is a Nash equilibrium, okay? If no player has incentive or desire to deviate from its strategy, given that the other players do not deviate. So assume we halt the game, no one changes. Now you can change. Do you want to change your state or not? Do you want to do some other action to get better payoff or not? If yes, it's not equilibrium. You move. When you move, then we halt the game again and we check this for the other player. We do it for all players, right? So we halt the game, we check it for one of the players. That player maybe doesn't want to move. We halt it again, we check other players. If all of the players say, I'm good, I don't want to change, right? If everyone is satisfied and happy, this is Nash equilibrium. Okay? I think you understand the difference of dominant strategy and Nash, dominant strategy equilibrium and Nash equilibrium. In dominant strategy equilibrium, I can say they're dominant by its name. They're selfish, right? In Nash equilibrium, they might cooperate. They might be kind a bit. They say, if others don't move, I'm fine. I'm fine with it, right? So I think now you understand why it revolutionized finance. Because in finance we have a lot of duopolies and several markets, several companies in the market, right? For example, we have Google, we have Facebook, we have or Meta, we have OpenAI, we have different companies which are monsters, right? And each of which can be selfish, or they can say, okay, let's let the market be like this. If I don't deviate, you also don't deviate. Everyone consensus on some state, and everyone is happy with that. That's a Nash equilibrium. So we see that a lot in finance. They don't want to be dominant necessarily, right? So let me say. By the way, as here mentioned, every dominant strategy equilibrium is Nash equilibrium, but not vice versa. So it's inclusive. Nash equilibrium, the equilibrium that John Nash proposed, says that it covers all of the dominant strategy equilibriums, but the dominant strategy equilibrium misses some types of equilibriums, and I am proposing them. So he extended the notion of equilibrium. Okay, all dominant strategy equilibriums are Nash equilibrium, but not the other way around. Not the other way around. We might have some Nash equilibrium which is dominant strategy equilibrium. We might have some Nash equilibrium which is not dominant strategy equilibrium. Okay. Now let's go to equation 7 to see Nash equilibrium in mathematics. Okay. So it says, for all SI prime, right, the payoff of the ith player is greater than or equal to the payoff of the ith player. So the payoff when it plays a strategy SI star is greater than or equal to its payoff when it plays some other strategy. Why haven't I said in this? Let's talk about its details. Why haven't I said SI prime not equal to SI star? Can you say that? Because it's greater than or equal to. If you put SI prime equal to SI star, then the left-hand side becomes equal to the right-hand side. So that's fine. So you can consider the case where SI prime equals SI star because you have greater than or equal to. So we relax this and say greater than for all SI prime, including SI star, right? This payoff is greater than or equal to. And do you see this, the difference? Do you see here? S minus I also has a star. In Nash equilibrium. So in dominant strategy equilibrium, let's go back. S minus I didn't have a star. Equation 5, 6, equation 2, equation 3, equation 4. S minus I doesn't have a star. So basically everyone says that whatever the others do, I don't care. I wanna be dominant. In Nash equilibrium says, I want everyone to be happy. S minus I star, right? When he proposed that, at least we see in his movie that his supervisor was shocked. He said, you know that it's a very revolutionary idea. Do you know what you're doing? And he said, yes, I know that. Because the dominant strategy equilibrium was used, I think, for 100 years in finance. He changed it. So, okay. I think in the movie, they say it was proposed by Adam Smith. Adam Smith is a very famous scientist, okay, in finance. But he changed that by proposing Nash equilibrium. He said that Adam Smith was wrong. Okay, so Basically, equation 7 is, I think you see the difference, okay? And no one wants to deviate. So comparing this, we see that it doesn't have for all s minus r. It also, another important thing. So there are several things. First off, it has s minus I a star. Another thing is that it doesn't have for all s minus I. It's for s minus I a star. Okay. In other words, in the Nash equilibrium, all players are happy with their situation and do not wish to deviate from the equilibrium. Right? Now we have, again, two cases: a strict, also called a strong Nash equilibrium, or weak Nash equilibrium. In the strict Nash equilibrium, this is greater than, I think for this at least we should write not equal to SI star. Sorry about that. Okay. For weak Nash equilibrium, this is greater than or equal to. Okay. So what do I mean? What is the difference of weak and a strong Nash equilibrium in English? Assume we have a game, we halt the game. Now I see the player I. Does the player I want to change? If the player I pays some other action, will its payoff increase or not? If it doesn't strictly increase, if it strictly increases, of course that player should choose that action because the player is rational, right? Rational. But what if the payoff doesn't strictly increase? For example, where the player I is, its payoff is 3. If it does some other action, its payoffs will still be 3. So that player might choose that action or not, because in both cases, its payoff will be 3, right? In this case, it can deviate, but it cannot deviate as well. So based on choice, then this is weak Nash equilibrium, right? By the way, assume the player I can go to the action to the other action. Both actions have 3. If the player I stays there, the other player also stays there, will not deviate. What if the player I deviates and go to the other cell, to the other case, to still have the payoff 3? But if it does that, the other player will deviate to the previous cell again, right? In this case, the other case is not an Nash equilibrium. What do I mean? Assume this is one of the cases. By the way, by case, I mean the cell in the normal form, right? In the table, matrix table of the game. So assume player one, no, give me a second. So player 1, player 2, okay? Yeah. So what do I mean? Assume we are here. The player 2 wants here, for example, we have 3. Here we have 3 and 2. Here we have 4 and, let me think, 1. By the way, we'll see examples. I just want to tell you what here it is doing. So I have 2 here and 1 for player 2. If I'm here right now, the player 2 wants to deviate. Why? Because its payoff 2 is better than payoff 1. So it will move here. Now I'm in this cell. Assume this is 4. This is 1. Okay. Then the choice is player 1's, right? So here we have payoff 3 and payoff 4. Of course, player 1 wants to deviate. We will be here in this state, right? Now assume it is, let me think. 3.5. When I'm here, does player 2 want to change? What are the payoffs? 1.5. 1 is greater than half, right? So the player 2 doesn't want to change. Player 2 says, I'm good. And player 1 already chose that action. So they are both good. So this is a Nash equilibrium, right? We'll see more examples, right? What if this is not half? So this is 3.5. Then, of course, player 2 says, no, I want to deviate. 5 is better than 1. We'll go to this. Okay? In this case, choice is player 1's, whether to go to this or stays where it is. So 3, 4. 4 is greater than 3, so it will move, right? Do you see a cycle here? So it means that we don't have any Nash equilibrium. Okay. What if rather than 3 here, I have 5. 5 is greater than 4, so player 1 says I'm good. Player 1 or player 2 already chose this one, so they are both good in this cell. So this will be Nash equilibrium. What if now this case? What if what happens if it is 4? Now this becomes interesting. 4 and 4 are equal to each other. So player 1 is indifferent whether to remain here or go here, right? If it goes up there, we'll have a cycle, right? We'll have a cycle. But if it remains here, this is an equilibrium. And this is a weak Nash equilibrium, right? So as a result, although this is indifferent, this cell, top right cell, is not a Nash equilibrium because its player 2 is not happy with it. Although player 1 is indifferent for that. Everyone should be happy with that. Did you see that? So some cases, one of the players is indifferent. The other player, no, is not indifferent. If we go to the other one, then we'll have a loop. In this case, only the one that both of them can consensus on is the equilibrium. And if one of them is indifferent, then it becomes weak Nash equilibrium. Can you tell me what happens in this case? 3, 3, 4, 1, 4, 5. Let me think. 3, 2. Everything is the same as before, but rather than 1, I have 2 here. So let's analyze it. Player 2, if I'm here, start from one of the cells. If I'm here, player 2 is indifferent, right? Now, if I'm here, player 1 is indifferent, right? Now, when I'm here, the top left corner, player 1 choices player 1's. Player 1 wants to deviate. When I'm here, choices player 2's. Player 2 wants to go here, right? Now follow the arrows. Follow the arrows. What happens? Put something on the cells. I will end up either here or here or here. In all these 3 cases, both players are happy, right? Agreed? And they are So we have 3 Nash equilibria. Am I right? Which one? Top left? Top left corner. No. For this side, choice is player 1. So you should consider the payoffs of player 1. 4 is greater than 3. Once if we are here, player 1 wants to deviate. Agreed. Sorry. So you're right. I apologize. So we have 2 Nash equilibria. I apologize. The top left one is not Nash equilibrium because player 1 is not happy with it. Right? We might have several Nash. Now, in this case, in this game, are they a strong Nash equilibria or weak? Because of these indifferences, these are weak Nash equilibria. Am I right? Because they are greater than or equal to 2 is greater than or equal to 2. 4 is greater than or equal to 4. Not strict. Agreed? Yes. In this game, can you repeat your question? If we are in top right, okay? No, so moving in this direction is choice of play is for player 2. Moving in this direction, the choice is for player 1. Okay, so moving vertically, you should check the payoffs of player 1. Moving horizontally, you should check the payoffs of player 2. If it is a cube, if we have 3 players, each dimension is you should consider the payoffs of that player, which corresponds to that dimension. Okay? Did you get it? So basically, you can assume you put an ant in the table, and the ant follows the arrows. And the ant will end up on the equilibrium. This is the Nash equilibrium, right? Put an ant, and the ant follows the arrows. Yeah. Any question? No. The ant is helping us a lot in this course. Ant colony, Nash equilibrium. So, yes, this is what we found. Basically, what I explained is the algorithm for finding Nash equilibrium. I think I already explained that, but let's see some other examples. So a way to find the Nash equilibrium in a game is to start from one of the cells in the game matrix, one of them randomly, and move or deviate to an adjacent cell if the payoff of the adjacent cell is strictly or weakly greater than that cell. We do this for all cells and players and show the movements by arrows between the cells. The cells where the arrows converge to are the weak, strict or weak Nash equilibrium, right? So we might have multiple equilibria. Usually when they are multiple, I think they are weak. I'm not sure about this statement, but I think I'm right. When it is, let me think. I'm thinking about if I can find any counterexample. Oh. I'm thinking about this case. Is about this case. This is weak Nash equilibrium. This is a strong Nash equilibrium. We might have a strong Nash equilibrium. We might have a weak Nash equilibrium. But I think whatever I'm thinking, if you find any counterexample, let me know. But as far as I'm thinking, you might have the only equilibrium, Nash equilibrium, which can be multiple is a weak one. If it is a strong, it's only one, I think. But its name is also obvious. A strict or strong Nash equilibrium must be one, I guess. Okay. So an example of this is this. So we might have one strong equilibrium, Nash equilibrium, and one or multiple weak Nash equilibrium. Okay. Now let's understand Nash equilibrium by a movie scene. In the lecture 1, I talked about this movie scene, but now let's go into more depth. So understanding Nash equilibrium by the bar scene in the movie A Beautiful Mind about John Nash. So I don't know if you can see it properly or not because of the lights here, but there are a bunch of guys sitting in a bar. This is the player for the Nash character, John Nash, and the other ones are his friends. They're all mathematicians. And a hot girl enters the bar, okay, or a blonde girl, whatever you call it, a hot girl. Then they say, "Oh, look at the hot girl," and they wanna try flirting with her, maybe something like that. And suddenly, Nash, they are talking. One of them says that, I think this one, the left one, says, Nash says something, and oh yeah, sorry. One of them says, have you forgotten what Adam Smith said? Whatever we learned in school. Adam Smith says that everyone wants to get the best for themselves, right? So they say each of us should try to grab attention of the hot girl because we want to be dominant. We want to follow the dominant strategy. When they said that, suddenly Nash went into the deep thought and was thinking that maybe what Adam Smith said is not correct because of this example. He says that to his friend that what happens if all of us want to try getting the attraction from the hot girl? What happened? The hot girl, by the way, has some other friends too. You can see them here in this scene. There's some other girls, and but this is the hottest one. So the Nash says, what happens if we all go for the hot girl? Then he continues that we will all fail because the hot girl will of us, and because of that, then we will probably try to go after the other girls, who are friend of the hot girl, but they will also reject us afterwards. Why? Because they don't want to be the second choice. Right? Not any girl wants to be a second choice. So what do? They will reject. So we will reject it after all. So what should we do? Probably we should find another strategy. We should all ignore the hot girl, and each of us goes to one of the average girls. Then, in this case, we will all have a girl each. We will not be rejected. Do you see that? Why do I say this? I do explain this. By the way, I didn't make this move. I'm just okay. Why this? Because using these examples, you can fully understand what Nash is saying. By the way, it became funny that one of his friends says, "What the hell are you talking about? Whatever you're saying is that because you wanna push us to go for the average girls and you go for the hot girl finally." Yeah, but Nash says no. Adam Smith was wrong, and he left. When he was leaving the bar, the hot girl looked at him, thinking that maybe he wants to flirt with me. But the only thing that John Nash told him was, "Thank you for letting me find out this strategy," and went out of the bar. Okay, so then he worked in that movie. He worked on that, and months after he went and defended his thesis. By the way, I don't know if you have seen the thesis of John Nash. He published his idea in one single paper, and then his PhD thesis, I think, had only 24 pages or something like that. and he had only cited citations, two references, his own paper and the book of von Neumann, talking about game theory. So it was a very old and famous book about game theory, but von Neumann is very famous, one of the scientists. So he had only cited these two, because I don't know if you have seen, in contrast to engineering departments, where we should have a lot of pages of thesis, and we should have maybe hundreds of citations, otherwise they would not let us defend. When you go to pure math departments, it's completely the other way around. So, for example, professors do not put their names on the papers of the students. We do that. They do that a lot in engineering departments. I call that cancer of department, cancer of science, okay, academia. Another thing is, for example, I read somewhere that a student in a mathematics class came up with an idea, went to the professor and said, I solved this. The professor was shocked because I think it was female. She had solved one of the most unsolvable questions in the mathematics. And of course, if they were in engineering departments, the professor would put his name after her name and would publish it. But the professor helped her, and she wrote the paper with her own name. This is how it is in the pure mathematics and pure physics. But unfortunately, in engineering departments, we have cancer of academia. Anyway, that's one thing, one difference. Another difference is that they don't care much about number of citations and these things. If you go and see full professors, they might have 100 citations, right? Full professors. But our PhD students or master students in engineering have 500 citations, so more than a full professor in pure math. Also, I think there is another reason for that too, because less people in the world understand what they are saying, and also an interesting thing is that they don't care about the number of pages; they care about the content. Where were we? So I was talking about the strategy in this movie. Did you understand how different is the dominant strategy and Nash strategy here? The dominant strategy, they all go for the best for themselves, but Nash strategy says that let's go for the other girl. Now, if the players go for the other girls in this case, now we halt the game. Do they want to change? No, they say, I'm good, I have a girl, right? So they will not change. So this is Nash equilibrium. And now let's see an example of a game with two players, each of which has 3 actions. The same game that we have. Now we should draw the arrows in the table, right? Let's see. So A1, A2, A3, B1, B2, B3. So let's start from one of the cells. You tell me, which cell do you want? Yeah, it doesn't. What? 13.3 here. You can even start from the middle, doesn't matter. But you should cover all of the cells, right, at the end. And you should have arrows between every 2 adjacent cells, okay? So, by the way, we don't have diagonal movements, right? You understand, because the players should play the actions. So, one by one. So here, for example, 13.3, now if B1 to B2, so for going to B1 to B2, 3, here it is 4. 4 is greater than 3, so B1 moves here. From here, 1, 4. Which one is, so 4, comparing B2 and B3. 4, 3. 4 is greater than 3, so we have this. Now comparing A1 and A2 in this cell. 13, 4. 13 is greater, so we have this. Now comparing A2 and B2 in this cell. You understand what I'm doing? That I'm comparing every 2 pairs, every 2 cells, adjacent cells. So here, for example, 4, 3. No, sorry. 4, as I said, don't be confused. For moving vertically, I should consider player 1, right? So payoff of 1, payoff 3. So I move in this direction, right? What about these two cases? 2, 3, I move in this direction. So what about these two? So 13, 4, I move in this direction. These two, -1, 4, I move in this direction. These two cells, 1, 3 is greater, so I move in this direction. And if you compare all of the cells with the same way that I told you, you will end up with these arrows. Now put an ant on the table on the cells. You will see that if I'm here, player 2 deviates. Player 1 is happy. Player 2 deviates. Then when I'm here, player 2 is happy from both sides here. But player 1 is unhappy, deviates. End up here. When we are here, both player 1 and player 2 are happy. Now consider other cells. At least in other cells, one of the players is unhappy. The only cell where everyone is happy is here. And it is a strict Nash equilibrium. I think you can guess why. Because this was also a strict dominant equilibrium. Dominant strategy equilibrium. We saw that in previous slides. It is the same game, right? And we just saw that all dominant strategy equilibrium are Nash equilibriums, but not the other way around. Agreed? Agreed. So now consider this other game where we have also weak equilibrium. So consider this 0, 0, -10, 0, 0, -10, -8. If I'm here, 0, 0, player 2 is indifferent. If I'm here, 0, 0, player 1 is indifferent. If I'm here, player 2 wants to deviate. If I'm here, player 1 wants to deviate. So this cell is a strict Nash equilibrium, A2, B2. It's a strategy, and this is the payoffs of the strategy. And this cell A1, B1 is a weak Nash equilibrium with payoffs 0 and 0, right? So basically it means that you understand that we might end up with weak equilibrium, right? When we have both weak and a strict Nash equilibrium, does it mean we necessarily go to the strict Nash equilibrium? No, it depends on what players do in this cell. If when we are in weak Nash equilibrium and they are indifferent and they don't move, they will stay there. They will stay there, right? Did you understand? So, where were we? Yes, we talked about this. Okay. We have some other examples, but let's talk about them after the break. Let's come back at 17 to 9. Is that good? 17. I don't know, 17 minutes to 9. Thank you. Okay. So, okay. So, continuing where we were, just before saying the examples, let me tell you one other important thing about Nash. That do you know what was his recommendation letter? So when he was going to get admission for PhD, we should have recommendation letters, right? Years later, years ago, actually, it was revealed that his recommendation letter by his supervisor for John Nash had only one sentence, only one sentence, that he's a genius. So only one sentence, he's a genius. That's it. Okay, so let's continue. Examples for dominant and Nash equilibria. Equilibria for the prisoner's dilemma. So let's see, for example, here, let's first see the Nash Nash equilibrium. Then, for example, consider this is the game, right? In the top right, you'll see the calculations for the Nash equilibrium. If we are here, -1, 0. 0 is better, so we have the arrow is toward here. If we are here, -1, 0. 0 is better, so we have an arrow toward down. If we are here, -3, -2. -2 is better, so arrow is here. If we are here, -3, -2. -2 is better, so arrow is here. So let me clean this. By the way, I didn't explain the game because we already talked about prisoner's dilemma and standard games in the previous slide deck. Okay, so now as you see, following the arrows, we end up in this cell, and that is a strict Nash equilibrium, right? So what does it mean? If you are under arrest and your friend is also under arrest, what should you do? Both of you should defect. Okay, we should not cooperate. Maybe it's not good to be recorded. This is what the game is saying. Nash equilibrium is saying. Okay, although it seems weird, but Nash equilibrium says that. And what about dominant equilibrium? So prisoner 1, prisoner 2. So consider prisoner 2, for example. Then this and this, these two columns. Of course, we should look at the payoffs for prisoner 2. 0 is better than -1, -2 is better than -3 strictly. So we get rid of column 1. We'll have this. Now about player 1. -3, -2. -2 is better strictly. So we get rid of row 1. We'll end up with this. Interestingly, both defect is both strictly dominant strategy equilibrium and a strict Nash equilibrium. Okay. Another game of chicken. Now we want to see what you should do if you get crazy and you want to try the game of chicken with your friend or your enemy, whatever. So you sit in the two different cars and you drive toward each other. Don't do it at home, right? So you drive toward each other. Then what happens? Teenager 1, teenager 2. So we have consider the top right corner, which is calculations for the Nash equilibrium. Here, -3, 0. 0 is better, we go down. Here, -3, 0. 0 is better, we go right. Here, 2, 1. 2 is better, so we stay there. Here, if you are here, we go up. Now about here, 1, 2. 2 is better, so we go left. So let me clean the whole thing again for you to see what's happened. Following the arrows tells us we have two, interesting, we have two strict Nash equilibrium. So this is the counterexample that I was looking for. Okay, do you remember several minutes ago I told you that if we have a strict Nash, it must be 1. Just this counterexample proves me wrong. Okay, so we might have two strict Nash equilibrium. Okay, so basically it means that one of you guys should be rational, and you shouldn't both be crazy and drive toward each other. One of you guys should be careful and swerve. Otherwise, you both die, right? But if one of you guys swerve, the other one shouldn't swerve, right? Otherwise, you both lose. So when one of you guys swerve, the other one continues. So this is exactly what Nash equilibrium says, and it makes sense. Makes sense. What about dominant strategy equilibrium? Let's see. If we are here, -3, 0. So, sorry, I apologize. Consider column 1, consider player 2. Column 1 and column 2. So we should look at these payoffs. 0 is better than -3, but 1 is not better than 2. So neither column 1 is better than column 2, nor column 2 is better than column 1. Now consider player 1. Consider player 1. I consider these payoffs and these payoffs. 0 is better than -3, but 1 is not better than 2. Again, neither row 1 is better than row 2, nor row 2 is better than row 1. So we can't do anything. We can't eliminate any row or column, right? As a result, we don't have any dominant strategy. Did you see what Nash did? Before Nash, people would say there is no equilibrium. Nash said there is. You can't see it. If you see with my eyeglasses, you will see that there are actually 2 Nash equilibria. That's why he won the Nobel Prize, right? He discovered hidden equilibria in the game. Okay. Equilibria for grab the dollar. So contestant 1, contestant 2. Let's see. First off, let's talk about Nash equilibrium. So if we are, by the way, here, whenever it is Nash equilibrium, we usually draw a rectangle around it. Also, doesn't matter. So consider here, if we are here, 0, 0, indifferent, right? See my cursor. Here, if you are here, 0, 0, indifferent. If you are here, 1/2, 1 is better. So arrow upwards. If we are here, 0/2, sorry, 1/2, 1 is better. Arrow is leftwards. So these are the arrows. As a result, these, they're all weak Nash equilibrium. Because if we are here, we are indifferent, right? If we are here, indifferent. If we are here, indifferent. So we have 3 weak Nash equilibria. What does it mean? If you are in a game, TV show, or grab the dollar, and they don't find you if you both grab, right? And if the payoffs are like this, you both either should grab rationally, right? Or one of you grab and the other one doesn't grab. If you do each of these 3 strategies, you are both doing rationally, according to Nash. Okay. By the way, if you learn mathematics and go to these TV shows, you will, with high probability, you will win, because many of these TV shows follow mathematical challenges. Okay. So try to learn mathematics and then go to these TV shows. So this one now, so dominant strategy equilibrium. So consider consistent 1. Let's see, 0, 0, 1/2, 0, 0, indifferent. 1 is better than half. Give me a second. What am I doing here? Did I make a mistake here, guys? What? Yeah, I think I made a mistake. Okay. 1 is better than half, but 0 is not better, strictly better than 0, right? As a result, we get rid of row 2. So I should erase it. I should correct it. We get rid of row 2. Let me correct it here. Grab. By the way, never be afraid of making mistakes. I'm not afraid of that. So 1, 0. Now you tell me. You compare these 2. So 0, 0. Indifferent, right? Indifferent. Then what should we do? So either we get this cell or this cell, both of these. So grab, or grab, not grab. They are both weak dominant strategy equilibria. Why? Because here we had greater than or equal to, right? So it's not strong. What about considering consistent 2 first time? So this 0, 0, indifferent, 1 is greater than half. As a result, we get rid of column 2. So this time I didn't make mistake. So this is correct. And now this is for indifferent. So again, grab, grab, or not grab, grab. So this one was also grab, grab, not grab, grab. As a result, if so, did you remember I told you guys, we don't care which player which start with for dominant strategy equilibrium. It just proved my word. We started with consistent 1 or consistent 2. We, in both cases, we ended up in the 2 weak dominant strategy equilibria, which are grab, grab, and grab, not grab. Yeah, right? Agreed? Did you understand? Okay. Acknowledgement. Some slides of this slide deck are inspired by teachings of Professor Stanko Dimitrov at the University of Waterloo, Department of Management Science. Also, this book, Games and Information, An Introduction to Game Theory by Erik Rasmussen. Again, William Spaniel has a good playlist on game theory. An important scholar in the area of game theory is also Martin Osborne. And these are the references, and you can see the papers of John Nash. John Nash, Equilibrium Points in N-Person Games, 1950. The Bargaining Problem by John Nash, 1950. Non-cooperative games, I think 1951. I think this was the paper of his thesis, I guess. And because of this single paper, he won the Nobel Prize, I guess. I think it was. I'm not sure, but I think this was the. And you can see that this paper has been published in Annals of Mathematics, the most important journal in mathematics in the world, right? Annals of Mathematics. So usually the journals which start with annals, such as Annals of Statistics, these are the most important journals in the science. Also, Annals of Statistics is very important. So John Nash, 2-person cooperative games, 1953. And you can see around those times, which was his PhD time, mostly he was thinking about games. And this is also Osborne, the book of Osborne, as I said, A Course in Game Theory in MIT Press. Okay, let's go to the next thing. The next thing, I hope I can finish it. I'm not sure, but let's try. I think we can't finish it today, but at least let's start it. Bayesian Nash equilibrium. I can say it's not that much straightforward as the previous 2 equilibria that we talked about. This one is a bit a pain in the neck, okay? but with some effort, it's understandable. So I gave you a warning for focusing on this one. And if you find it hard to understand, know that it's also hard to understand for me. Not just for, okay, it's a bit weird. You'll see. Okay, Bayesian Nash equilibrium. Sequential move games. Let's first talk about sequential move games. In ordered or sequential move games, the players play the game in order. So they don't play the game simultaneously. It's an ordered game, okay? Recall that an ordered or sequential move game can be represented by an extensive form or a game tree. Do you remember? We talked about it. There is an important thing in sequential, specifically in the sequential games, and that's common knowledge. It refers to the assumption that, please focus on this. So it's a hierarchical thing. Each player knows that the game tree, what the game tree looks like. Again, each player knows that other players know that what the game tree looks like. again, we go with one more depth. Each player knows that. Other players know that. Other players know that what the game tree looks like, and so on. Goes until infinite cases, right? So it goes depth by depth. Of course, this assumption is useful when all players play the game rationally. If at least one of them plays irrationally, then it's useless, right? Assuming that they play rationally, this common knowledge is useful. Can you remember what it reminds? Have you seen the Friends series? Who here has seen the Friends series? Yeah. Okay, great. So you are a fan of Friends, right? No, I'm a fan. I'm a fan. Friends is very great, especially whenever you find yourself in depression. Watch some episodes of Friends. It helps. It helps. So this reminds us of the episode, the one where everybody finds out in the Friends series. Let me tell you what this episode was about. So there are several friends in this series, 3 males, 3 females. So the males are Ross, Chandler, Joey. Joey is a flirty guy who usually flirts with the girls and also loves sandwiches. And Ross is a scientist guy. Chandler is a guy who works in administrative offices, something like that. And the 3 females are Phoebe, Rachel, and Monica. So and they are friends, normal friends. However, at some point, Chandler and Monica fall in love, and they fool around, and they don't want the other friends know about it. So they try to hide it, but Joey finds out, and they tell Joey not to tell others. Gradually, Rachel also finds out. Rachel is this one, the left side in this figure. Hopefully, YouTube doesn't warn me for copyrights. I don't know. Because they're very restrictive on friends. Okay, so the left side is Rachel. The right side is Phoebe. Rachel finds out, then tells Joey that I found out. Anyway, later Phoebe also finds out by catching them having intercourse, and then what happened? Finally, they make a plan. As I see, it's very funny. So Joey said, okay, now many of us know. Let's go and tell Chandler and Monica that we found out. But Phoebe, which is the right side, female, says that let's not do that. Let's play a game with them. Let's say, let me flirt with Chandler. So he thinks that I have fallen in love with him. So we make him angry because he thinks that we don't know that he and Monica are fooling around. So let me annoy them in this way. And then, okay, this goes, so then Chandler and Monica find out. Then Chandler and Monica found out that Phoebe and Rachel also know. But Phoebe and Rachel didn't know that Chandler and Monica know. Suddenly they found out, Phoebe and Rachel found out that Chandler and Monica know that they know. Okay? Then they want to continue this game to see which side wins. Then in this scene that I put a screenshot of, Phoebe says something very funny. Says, they don't know that we know they know we know. Okay? They don't know that we know they know we know. I bet she had practiced this sentence a lot, otherwise she couldn't say that. And then funnier thing is that they faced Joey, this is a scene where they face Joey, saying that Phoebe says, they don't know that we know they know, we know. Joey, you shouldn't say anything about this to them. Joey said, I couldn't if I wanted to. Okay, it's too complicated. Anyways, that was a fun scene, and this is about the common knowledge. So we know that they know that we know that they know that we know that they know that, right? Okay. So moving on. So certain symmet. Do you like it when I refer to the movies and certain? Okay, great. Okay. Certain symmetric and complete games. So recall that nature can be one of the players which makes random movements with known probabilities. Do you remember? Nature was a non-strategic player which makes random movements with known probabilities. Certain game in the literature is that when nature does not move after any player, but it either does not participate in the game or it starts the game. Okay, this is called, in the literature they call it certain game. So nature either doesn't play or it starts before the players play the game. So what does it mean that the nature starts the game? It means that we have different realizations of the game, and then nature decides which one. For example, we have duopoly of two players, two big companies such as Google and Facebook in the market, but the nature decides whether we have recession or not. The realization or the state of the game, okay? Then the movements, the rational movements of the players will differ depending on the situation. So symmetric game is when no player has information different from other players when it moves or at the end nodes of the game tree. Okay, so when the players have the same information, this is a symmetric game. A complete game, by the way, I'm just telling you some terminologies, so if you see them in the literature of game theory, you know what they mean. Complete game means nature does not move first, or its initial move is observed by every player so that all players know what situation the game is in. Do you understand what is it? So it says either it does not move first, so it's in B. So maybe player one starts, and then nature decides the situation, and then player two does the play action. It's a sequential game, right? Or that, or it moves first, but everybody sees that. Because when it is a sequential move game, the player one usually sees the situation, decides, and then the player two sees the action of player one. The player two might not necessarily see the action of nature. Okay, because it's a sequential game. So a complete game says that even if the nature starts first, all players will know the situation if it is a complete game. Okay, these are just some terminologies. Now, Bayesian Nash equilibrium. I don't know how much I can cover, but let's go. Okay. Bayesian Nash equilibrium, it was proposed in 1967. A bit old, okay? References 1 and 2. Considers some probabilistic beliefs for every player. By the way, whenever in the literature you see belief in means probability. Okay, don't get worried. See what belief means. So in machine learning also, whenever they say belief, they usually mean probability. Okay. So, for example, an example of belief in machine learning, restricted Boltzmann machine. We talked about it when we were talking about simulated annealing, right? Belief. So also factor graphs in statistics, they talk about belief, it's probability. Therefore, it is useful if there is some randomness in the game, such as when nature plays a role in the game. So when is Bayesian Nash equilibrium useful? When we have some randomness in the game. If we don't have any randomness in the game, should we go for Bayesian Nash equilibrium? It doesn't make sense. Its name says it uses Bayes. What is Bayes rule? It talks about probability, right? When the game is deterministic, it doesn't make sense to use Bayes and Nash equilibrium. So it makes sense when the game has some randomness. When does the game has some randomness? Can you tell me? According to whatever we have said so far. What? Nature. Whenever we have nature as a non-strategic player in the game, we have randomness in the game. As a result, whenever we have nature in the game, maybe Bayes and Nash equilibrium makes sense to use, right? To be used. Moreover, note that Bayes and Nash equilibrium is usually used for ordered or sequential move games. So every player assumes with some probabilistic beliefs that the other players will have some strategy in playing the game. So everything is probabilistic here. Every player has some probabilistic beliefs that what other players will do, what strategy they will choose, okay? They might not choose that necessarily, absolutely. It's just random. It's probabilistic, okay? Then while the players play the game one by one during the game, the players update their beliefs using Bayes rule. So what do I mean? It's a sequential move game, right? So initially, everybody has some belief. When player one starts playing, player two updates its beliefs. If we have three players, player three also updates its belief. So the players update their beliefs based on the actions of other players. So let me tell you an example. Assume there is a competition between Google and Facebook. Maybe, let me think. Maybe outputting chatbots. OpenAI, between OpenAI and I think that we see that nowadays, between OpenAI and Google. OpenAI wants to develop ChatGPT and Google wants to develop BART, right? BART? BERT? No, not BERT. BERT is something like BART. BART. BERT, I know what BERT is, but Google, BERT is not. BERT is a stack of encoders. Let me tell you briefly what these mean. BERT is a stack of encoders of transformer. GPT is a stack of decoders of transformer, because transform is an autoencoder. It has encoder and decoder. For BERT, they said let's get rid of decoder and only have encoder and stack it. Became BERT. Many phone companies, that I don't want to say their names because it's been recorded, they are using BERT in their cell phones as embedded systems. Okay. And the other way around, if you get rid of the encoders and have the decoder and stack them up, it becomes GPT. So we have GPT-1, GPT-2 has more layers, it becomes bigger and bigger, and ChatGPT is based on GPT. Okay. So everything is about transformer, and everything in the transformer is about attention. So attention mechanism is nothing very, I think we don't have much time, but let me tell you this. Attention, I think you know what it means, right? In parentheses, it's not related to game theory, by the way. What is attention mechanism in machine learning in a nutshell? I told you once, did I? No? Assume you are in Louvre Museum, I think, and you are looking at the Mona Lisa portrait. Am I right? By Leonardo da Vinci, am I right? So, what do you look at when you are looking at Mona Lisa portrait? What? Mona Lisa. What? Usually, where do you focus? Maybe her face. And where do you focus more? Maybe her lips and a smile, right? Do you curve in initial glance that there is a river behind her? No. So you attend to the picture differently, right? Another example. So this was picture, image. Another example, text. When you are doing fast reading, so you have 100 pages of 300 pages of Harry Potter. There were some competitions for fast reading of Harry Potter, I remember. So you have 1 hour to finish the whole novel. Okay. And then we had those competitions at that time, I remember. And then what do? Do you read every word? No. You drop some words from your attention. You don't care about they. They is something I think redundant in English, right? Like al in Arabic. We see this a lot in words. Get rid of the, get rid of am, is, are. Important things. For example, the sentence loan, Mona Lisa is a portrait painted by Leonardo da Vinci. In this sentence, only Mona Lisa. Maybe portrait, maybe with less attention, and Leonardo da Vinci are important. The other words are crap, right? So get rid of them when you are doing fast reading or skimming. When you skim, you should get. It's a good technique for reading papers. Okay. So this was an example in text. As you see in both text in image, you wait. So when I say you attend to some pixels, like the pixels around the lips of Mona Lisa, or to some words in the sentence, what do I mean? How can I model it mathematically? It's just waiting, simple waiting. Let's weight the pixels, where the weights they get bigger if I need to attend to those pixels more, right? Or give each word a weight, and if a weight is larger, it means that that word is more important. And then you can add them up, right? So this simple weighting is called attention. By the way, in another perspective, you can explain attention mechanism by query retrieval. Have you passed any database course? No? Maybe. Okay, so if you have heard of hash tables, okay. So soon we have a table with keys and values, okay, in memory, keys and values. So some query thing comes and we should see, so we have keys, key 1, key 2, etc. Value 1, value 2, etc. Then a query comes, Q. Then there are some techniques to check query with each of these keys very fast. So if you don't do it in a fast way, your time complexity is awful because the table might be very large in the computer. Assume it's a RAM, okay? It might be 1 million entries. Then you need to go one by one. But they have developed some technique named hash code or hash table, okay? That they check it very fast. Anyways, we don't care about hash for now. We check and we find the corresponding key. For example, key 1 corresponds to Q, to the query. The retrieval is its corresponding value. We'll retrieve value, okay? I think you see it's use case in RAM, right? We use it a lot in every day you are working with your computer, you're using that. So this is how we do that. By the way, in Python, this hash table is implemented by dictionary, dict, okay? So you do that, and then now one might say, why do I check this with one key and retrieve only one value? Why can't I say how much similar this Q query is to each of the keys, get some weight, and use those weights for the linear combination of all of the values? So rather than hard retrieval, let me have a soft retrieval. Did you get it? So let me say, for example, you see query is very similar to key 1, 0.9 score, but it's a bit similar to key 2 also, 0.1, and the other weight is 0, assume, okay? Then the retrieval will be 0.9 times value 1 plus 0.1 times value 2. This is called attention. Now, can you tell me, maybe last sentence, can you tell me how can we calculate this similarity or this weight? How do we calculate similarity in mathematics? Cosine similarity. Cosine similarity is a normalized inner product, right? So maybe inner product. Now, whenever you're using ChatGPT, it all reduces to inner products. What do I mean? Every word in the sentence, we see how much is this word is similar to other words in the sentence, right? So we calculate how much every word attends to other words in the sentence, right? And by the way, GPT, its output always goes to input with a shifted way, okay? Now you understand why when you are talking, we're chatting with a chat GPT. For example, you say, hey, chat GPT, my name is Benjamin. You go after 5 minutes of chatting, you ask ChatGPT, by the way, what was my name? It will answer you, it was Benjamin. It remembers because of this shifting. Because of this shifting, it remembers what it was talking about. Okay? And in a nutshell, I told you how ChatGPT is working nowadays, right? So now, whenever you use ChatGPT now, use it in another perspective. You know that every word is attending to other words by some ways. Why did I say this? I don't remember it. Anyway, we will continue Bayesian Nash equilibrium in the next session. Okay. By the way, after Bayesian Nash equilibrium, we have mixed strategies, which I said the probability of playing actions, and then we have continuous strategy and some examples of continuous strategy. Who is from management science or finance? Finance, management. You left? Okay, so that one is it might be very interesting to them. So people in management science, you might like it. It's about also duopoly. We will talk about, let me tell you. So these ones, Cournot competition, Stackelberg competition, and Bertnard competition. These are important competition models for duopolies, such as Google, Facebook, in markets. And it's very useful for people in finance and management science. Okay, great. See.